We can start with our guest, the final guest this semester in our Transregio seminar, and that is Toon van der Bremer. And he's a professor, full professor at Delft University, Technical University of Delft, in the Department of Civil Engineering and Geoscience. And he's also professor in Amsterdam, associate or adjunct professor, I guess. And previously he was in, well, there's a long list of
I'm over 3 years. Yeah.
Of oscillating between Edinburgh and Oxford, back and forth for some time. Also doing your PhD, right, in Oxford, I think.
That's right.
And as a postdoc in Edinburgh and postdoc in Oxford, and then he went to Delft as a professor, working on surface gravity waves, apparently, and also other waves, internal waves, all kinds of waves with all kinds of methods and tools. And this time you will tell us about tank experiments, right?
That's the plan.
Rotating tank experiments.
Indeed, that's the plan.
Interesting.
So thank you, Carsten, for the kind introduction, and thank you, Carsten, Lars Silova, for inviting me to give a talk. This is work that's indeed taken place over a number of years, so quite a number of people have been involved in it. The main bulk of it is a current PhD student, Jessamy Moll, but it started off thinking about this problem together with Chris Higgins, who I think you know, and because he's here now, he was a PhD with myself and Jack Van Nest, who you also know. The title is Wave-induced drift on a rotating Earth. I'll show tank experiments, but I think I'll introduce things. So I'll share my understanding of the theory, the relevant theory, and maybe even some global based simulations, just to try and tell at least a complete story, partially true perhaps, but at least complete, about what happens when waves transport things on a rotating Earth. So I put up a picture for Chris, because I know from my experience that he would always be 5 minutes late. Sorry. In fact, this is actually, Chris, it's very nice to see you. It's actually good. This is good. When Chris was younger working with me, I think it was more like 10 minutes. So I think it's... I put this picture up of Chris because I thought it'd be funny. And I thought at first we'd look at how Chris has aged. I've now seen that he hasn't aged. So now it's pretty much the exercise is on Chris to work out how much I have aged, but he won't tell me because he's too polite. So I'll share, I'll start with a video. Oh no, I won't put on the impressive sound that I put on. So this is a video of the experiment, the facility that I would like to, where do I stand? I stand here, that I would like to show some initial results from. And it's a facility we built at the TU Delft over the last 3 or so years. And it's a facility that combines, as you can see here, surface waves and tries to increase the effects of the Earth's rotation so we can actually measure it in the lab.
There's a wave maker on the right side.
There's a wave maker on the right.
It's like a pedal.
It's like a paddle that you can control to basically generate a spectrum or a periodic wave. On the other side, well, you can't really say left and right with this, but here, temporarily on the right, absorbing beach. That's trying to at least absorb the dominant. And here you can see a zoom out of this in our laboratory at TU Delft. We've named this the Delta Transport Processes Laboratory, because anything at the TU Delft has delta in its name, so I thought that was important, because the focus here would be to understand properly really transport processes that occur close to the coast and hence in deltas. But that's a facility, but I'll sort of end. I'll end on this again. So I've written down a couple of questions that I wanted to sort of try and partially answer, and these questions start with. First of all, from a theoretical perspective, what's the effect of the Earth's rotation on surface gravity wave-induced drift, starting in deep water? It's a story of a Stokes drift, which I think many of you will have seen, but not everyone here in this room, and also the anti-Stokes drift, which is an opposing flow that very few people know, and I think here in this room, quite a few more people than usual know. Then the second question, this is a question that basically Chris maybe has already given a seminar on, so I might repeat some of the things that he found. Then I'd like to talk about, can we actually observe this in the laboratory, using a different facility from the one I actually showed you for the prototype, showing a little bit about the real world, what's the effect of this actually on global wave-induced drift patterns, so that's predictive, and then a bit of a review about what do I know as to the observations of this phenomenon called the anti-Stokes drift, which I'll have to introduce. Finally, some new stuff, some unpublished stuff on the effect of unsteadiness and of the wave forcing, and find out depth on all of the above, and then the very, very end, some measurements of the drift across the whole water depth using this facility that I showed you a video of. So I'll start with the first. This is an introduction slide. I think a result that actually required, this is a slide Chris made kindly for me 5 years ago, but a slide, of course, that I don't really need to repeat. So we all know wind-driven Ekman dynamics. We have the notion that there's a wind. So in this case, there's a wind in the x direction. This drives a spiral. And in principle, that's an unsteady problem. So the simplest possible way to think about that, if I use a stick, there's an unsteady term, an accelerating term, there's an IFU, and then there is some sort of mixing term with a viscosity here, which you might set as constant for a simple model. And then finally, there is a surface boundary condition. If you solve that problem, you get this sort of spiral that evolves in time towards a steady state. And this happens with wind, but many of the physics in this problem, and they also can occur with waves. And that is what I'll show you. At the same time, there is a phenomenon called Stokes drift. So this is now no rotation of the Earth, just periodic surface gravity waves. This is an old picture from the album of Fluid Motion. So it's probably the only really good image of Stokes drift that many people know. And this is a picture of pure progressive surface gravity waves. So at the surface, you don't see all these periodic waves, and you see these circular orbits of a Lagrangian particle here. And if you look closely, you see that specifically near the surface, the orbits don't close. So there is a net transport by these waves from left to right. That's known as Stokes drift. So this is an old, really, really old image, probably the first image of maybe Stokes drift. So the calculation to do Stokes drift is sort of an undergraduate little work problem. And what you can do is you can say, I have a position of a particle, a Lagrangian position, that I just have to solve subject to some flow field. And the flow field I take from linear wave theory. If I do that, I do a sort of expansion, and I expand out the dependence on position using some expansion in the small parameter, which is the steepness of the wave, some product of amplitude and wave number. You can show that there is a mean transport that's associated with linear waves. That's the Stokes drift, which is a product of the amplitude squared, the frequency of the wave number, and typically has an exponential dependence as e to the 2kz in deep water. So rapidly varying with depth. And if you are more graphically minded, here is a little video of what a particle would do. So you can do a little undergraduate class, and you can code this up. And you see here the x position of a Lagrangian particle on the x-axis and z position on the z-axis. And in blue, you see the free surface of the wave going up and down. So this is quite zoomed in. You don't actually see the spatial sinusoid that is the wave, because it's quite zoomed in x, because it's focusing on a small trajectory. But what you mostly see here is that the particle goes through these sort of circular or close to circular orbits, but it moves from left to right. And that phenomenon here in this little calculation is the Stokes drift. But it's important in all of this, when you think about what particles actually do in the ocean, to think about Lagrangian. So it's important to think about whether there's any mean flow also in the Eulerian. So this mean flow here, this Stokes drift, is not present in if I do Eulerian averaging, only present in Lagrangian averaging. So it's this sum that matters. And when we do things in the lab, we always have to ask ourselves, is there also a Eulerian mean? Because otherwise we might get the wrong answer. And particularly rotation, which I'll show in a moment, will interact with waves in a way that I'll explain to give rise to a Eulerian-mean flow called the anti-Stokes. But before I go to rotation, a quick sort of really quick one-slide review of what we typically do in the lab when we are interested in measuring the Stokes drift. So typically what we do is we have these facilities, which some of you might have seen, wave flumes. So a facility that's basically like a long, narrow swimming pool. And at one end, we have some kind of wave maker, either a piston or some more complex structure. As you can see here, this is an image from the University of Plymouth, where some of this earlier work was done. And what we then do is we take measurements, but we never actually only measure the Stokes drift. So we have to be really, really careful with that. And in this particular case, we, in general, without rotation of the Earth, without the effects of viscosity, typically you get Eulerian-mean flow because of either closed boundaries. So this is a box. So if you have Stokes drift from left to right, it will have to come back somehow. Or you get it from spatial variation of the wave field. And both of these are sometimes called a return flow. And typically in a lab experiment, what you get is that this return flow is simply the depth integrated version of the Stokes drift with opposite sign. So basically the flow comes back, but in a depth unit way. And if you do wave group experiments, so a couple of waves, so you have no build-up meaningful boundary layers, you can actually, rather than observing the velocity, you can actually observe the net transport. So this is the net horizontal transport by a wave group. And red here is the theory and black are experiments, theory of just the Stokes drift and this return flow. And what you see here, 0 is here, you basically see this picture of a lot of forward transport. This is this e to the 2kz, a lot of forward transport here, and then a tiny bit of negative transport at depth. And if you were to depth integrate this curve, typically, at least in deep water, it integrates to 0. So that's the kind of the picture in the laboratory.
Can you explain the second point is why there is a return flow by spatial variation of the wave field?
Right, I can. So if you have say a wave group, so a couple of waves that basically a wave, periodic wave that's modulated, say by a Gaussian, then at a physically then also the Stokes drift would be modulated by that same Gaussian, and the Stokes drift therefore is growing and decaying. So it's growing and decaying, and that is, if you want to think of this in terms of a mass balance, that is basically sucking out water on the left of the packet, dumping it on the right of the packet, and that leads to a return flow underneath. So basically, if you have a wave group, you typically have a positive Stokes drift in one direction and a negative Eulerian return flow that returns that fluid underneath. So in this paper, we present this through a conservation of volume argument that you can do conservation of volume. Now, still reviewing, there's also a phenomenon called the Coriolis-Stokes force, but if we look at the historical literature, the starting paper on this, I think, is probably Ursel in the 1950s, who made a theoretical argument, which I won't repeat here, but he showed that for regular waves, periodic waves that are infinitely lived in a rotating frame, there can actually be no Stokes drift. And he showed, using an argument that I won't repeat, that there has to be this thing called an anti-Stokes law. I think the name came after, which means that on a rotating Earth, the Lagrangian transport, so wave average Lagrangian transport has to be 0. Therefore, there is a Eulerian-mean flow that is equal and opposite to the Stokes drift. And it's that identity here that gives rise to this definition of an anti-Stokes flow. And that was maybe firmed up a little bit by Hasselmann in the 1970s, trying to really introducing the Coriolis-Stokes force. You can see the argument here, a momentum equation with an unsteady term, a Coriolis term. And if you ignore the pressure gradients and you do a second order calculation, which is already partly given here, then Hasselmann's result, which copied from the paper, is that without viscosity, with waves and with rotation of the Earth, he said that the sea is basically full of undamped inertial oscillations. So what you have is that these Eulerian-mean flows are basically the initial condition plus this sort of convolution type operator, this sum of all the previous Stokes drift and their interaction with air, which is the solution to this equation with the pressure term turned off because it's completely linear. So that's kind of the Hasselmann world, is that you have all these inertial oscillations that are infinitely lived 1970. I'm just sort of throwing equations on the board without really properly showing where they come from, but there are this equation set called the Craig-Leibovich equations, which describe basically mean flow interaction with the Stokes drift. And you can write a set of equations which are written here from Chris's paper from some years ago. And basically, these equations are simplified to second order and steepness. A lot of spatial variation is thrown away, and such that we get a really, really simple set, which sometimes is referred to as the Ekman-Stokes equation. So physically, what do we have here? We have momentum equation in the x direction, y direction, and z direction, and we have a constant resistance. That's the whole set, and the only physics that's included is a Coriolis force, some unsteady derivatives on the velocity, and the possibility of having viscosity here such that there is a dissipative process of momentum, dissipative process going on. And what you can actually write this, you can write this in complex notation because the Z structures are the same. So you can introduce these complex horizontal velocities, U plus IV, and then it's actually quite convenient to write these two in one equation. I think the only thing here to note is that basically this becomes this equation here, but you have to think about two other equations. One is a bottom boundary condition. So at large distances away from the surface, the velocity is zero, and the other is a wave stress equation. So this says that the Stokes drift provides some forcing on the system, and it's basically the surface boundary condition known as the wave stress condition, which I think I'll come back to later in my talk. So physically, what do we have? Again, we're just adding the arrows. We kind of have three characteristic scales in this problem. And if we start from the top and go towards the bottom, first we have a really thin surface boundary layer, which I think the analysis of which dates back to Lagrangian-mean 53, which basically comes from the molecular viscosity and it's wave driven. So it's the period of the waves that's there. So at the surface, there's this thin, really thin boundary layer, which has this delta nu definition here. In principle, there could be boundary layer streaming or other processes in there that we don't typically measure, we don't typically think about. Then there is the Coriolis-Stokes forcing, which is felt on 1/2K, so the characteristic depth scale of the wave field of the Stokes drift forcing. And then there is an even greater, typically scale, which is the Ekman spiral, 2 nu over f. And those are kind of the scales that play a role. And the work that Chris did at the time is that he said, well, if you look at this problem, you can actually solve this with the Laplace transform. So you can introduce a Laplace transform. The details of that calculation I'll spare you. But then you can actually solve for the Eulerian-mean flow, and you can actually work out that problem. And I'll show you some pictures because the graphs, the equations themselves, I have no time to really talk about. But what you can also do is recover a well-known steady solution to the problem where you have a forcing that's steady, but we wanted to actually understand the unsteady problem. I'll show some pictures in a moment to really explain to you the physics. So here is the kernel that he said, well, you can solve the problem and then you can write it as basically a convolution with a Stokes drift forcing that varies in time. There is a slow x dependence that does nothing because it's being ignored, but the z variation is solved for, and you can actually write this kernel. And what this kernel has, it has an Ekman spiral. For those working on this problem, this will be immediately recognizable, for others less so. And it has a Coriolis-Stokes type term. So there's these two terms that I think make sense. But I think it makes more sense to really plot this holograph of the kernel. On the x-axis, we have the real part of k, and on the y-axis, the imaginary part. And this is a little plot with some realistic geophysical circumstances. So the red numbers are the number of days. So this is the number of days. So we see that over, in this case, sort of 10 days, this thing spirals to 0. So we have inertial oscillations here. We have convergence towards 0, 0, and that's kind of what's happening. That's the physical process that this Eulerian-mean velocity should follow. Here is a picture that I'll have to take some time to explain. Look at the top, don't look at the bottom. And what this is an example of what would happen if we have a Gaussian storm. So a storm, basically a Stokes drift that follows a Gaussian. So the starting point here is US. US follows a Gaussian, I think here it's about 48 hours long, so a typical storm, then it's 0. So the storm is gone. The storm is in the x direction, so the waves go in the x direction. There's nothing in the y, so this is the y component, and this is the magnitude. So what then happens is that the Lagrangian transport is the sum of the Stokes drift and this u over bar, this flow that is driven by Coriolis, but has strong signature of anti-Stokes. So you have initially this opposing flow, so it's kind of anti-Stokes-like, and then long after you have these oscillations that are present after the forcing has long gone. And you see that the oscillations are no longer in the directions of the waves, you see them in both the x and the y direction. And if you make these windrows, which are now the bottom plots, basically trying to make a sort of histogram, I won't explain the exact details of the graphs, but a sort of histogram of the directions in which things go. The Stokes drift is in the x direction. Eulerian-mean u here, it has much more spread, but typically is at this angle of maybe 45 degrees or thereabouts, but not quite because it's unsteady. And then the Lagrangian flow has also got a distribution of angles. So basically, this is a sea of damped inertial oscillations that we predict. So that's theory. So our question was then, can we actually observe some of this behavior in the lab? Can we build a facility that allows us to see at least the anti-Stokes drift, but ideally much more the richness of the unsteady response in the laboratory? So this is a sort of sketch of the facility we built. It's very much like the video I showed, but it's at scale. This was the prototype at scale. So we have a wave maker here on the left. We have an absorbing beach here on the right. We measure the wave properties with wave gauges. And we put this 2.2 meter wave flume, so it's very tabletop-like. We put it on a rotating table. So we introduce an axis of rotation. There are many geophysical labs that have these turning tables. We put it on there. And what we do in terms of measuring things, we don't actually measure the flow field because we want to just get started in an easy way. We put small particles on the surface that are partially submerged, almost entirely submerged, but we still want to see them. And then we follow their motion as they typically, without rotation, would travel from left to the right through this sort of field of view of the camera. So that's the basic setup. And before we actually look at some results, this is what we expect to see. So here you see the experimental facility in plan view. So we have basically, there's a field of view here, which is a square box. And typically we put particles here in on the top left, expecting that without rotation, they would go to the right. And with rotation, they would probably go at an angle. So we kind of hope that this thing is wide enough for this to work. In reality, the solutions I presented have no x variation, have no y variation. So we're concerned about these boundary effects. So what would a particle trajectory look like? These are x and y, the horizontal coordinates. Well, without rotation, so there's a rotation of the table, we expect the thing to go from the left to the right, to a straight line. If we have no viscosity, but rotation, we expect a perfect circle. And if we have a combination of non-zero viscosity and non-zero rotation, we expect to see a series of loops that ultimately give rise to a mean drift that is less in magnitude, which you can't see here because there's no time, but it's less in magnitude than the Stokes drift, and that's at an angle. That's sort of what we expect to see in this simple setup. So here is a video. Let me see if I can play that. Of the experimental facility. Don't focus on the bit on the right that's behind the wave maker. So the beach is here on the right. You see the beach where the waves dissipate. The wave maker you can now see. Sorry, it's flap. We control, you don't see. Again, and the waves we don't see. You don't. Well, I think you see maybe some. Here you see them. Yeah. So this is now a video of what the camera that hangs above this facility sees, and this is without rotation. So this is, you see they're about 3-4 millimeters of bits of plastic that are close to the density of water. And you see that they oscillate a bit, so that's the oscillation of the surface wave field. And in this case, you can't really see because they move so slowly. Yeah, but they move in principle. If you average out over the oscillation, you see that they move from left to right. They at least move in the direction of the Stokes drift.
The previous slide you said you expect them also to move in the.
This is without rotation. This is without rotation, and I'm now going to show you one with rotation.
What is the reason why you expect this to also in another direction?
Right. So you mean this picture? Yeah. It's basically Coriolis. You have Stokes drift. So Stokes drift is in the x direction. I introduce Coriolis. I have then a Eulerian-mean flow that is at an angle due to the Stokes drift, and therefore the net Lagrangian transport is at an angle. So it's like Ekman spiral, but with Stokes drift instead of wind or wave forcing, wave stress instead.
The tank has a lid?
The tank has no lid.
No lid.
No lid. Yeah.
Does it matter that when the tank moves?
It's a good point. Actually, the tank does have a lid, and we do. Doesn't matter. But the particles are almost fully submerged. But if you choose particles that are a bit more buoyant, then you have to be really careful about wind flows and air conditioning and tiny things. But in principle, the airflow does not matter. We do the experiments with and without a lid. So either containing the airflow above or not containing it at all, and it doesn't make a difference. Yeah. But if you were to have chosen a lighter particle, it might have mattered. These particles kind of are 95% the density of water, so they're kind of almost completely submerged. And the waves are not forced by wind, the waves are forced by the wave maker.
And there's no circulation due to the waves. So if you do this kind of experiment,
yeah.
I thought you end up having this type of
good point. We have no
large scale circulation.
Good point. So first of all, I think the first thing we do is we spin up the facility without waves for a long time. So we wait until that's steady. So there are no initial transients to do with rotating flow. Secondly, then we set up the wave field, and in principle, one might expect there to be some development of some structures, but I think we see we haven't really carefully examined all the spatial locations, but we don't focus on and maybe don't see Langmuir cells. But I'll show you some results later on where maybe it's things like that, features like that play a role. Yeah. We'll come to this. So now this is a video with rotation, I think. So now the particles, I think I might fast forward a bit because the video takes forever. You see that now I fasted, so the particles have begun to move from left to right. In any case, this is what the raw experiments look like. And now this is what some of that process trajectory data looks like. So I'm showing you comparison between theory, Chris's theory, always in blue, and then the experiments in gray, left and right. And I'll start with the non-rotating case, where in principle the theory predicts in the non-rotating limit no drift, although there are funny limits. So forget about the light blue line. And indeed, the experiments show some. These are the sidewalls in the experiment, so they show some sidewall effects in terms of convergence of the flow, but basically the trajectories are the same. And then we introduce rotation, first slowly, then more rapidly, and then in the opposite direction. Right, and what we have first noticed that for the slow rotation, the theoretical prediction of the size of this Stokes-Ekman spiral, it doesn't fit in the tank, right? So we kind of expect this to be difficult to see because in the model there's no boundary conditions like there is in the lab. Indeed, we see things moving at an angle, but we struggle to really see the beginning of this sort of spiraling effect, these loops that are they're inertial oscillations. If we speed up the table, where we expect to actually have smaller inertial loops, experiment is much messier, but we see clearly evidence of these loops. We also see clearly evidence of movement at an angle, maybe not the right angle. Reverse the rotation. The thing is basically, well, this is double and reverse, but it's basically, you would expect there to be just a mirror image here, and we see something similar. What I'm showing you here is 3 theoretical lines, and I'll come to this in a moment. This is at least a sort of sense that, at least very quantitatively, things might look like you expect. Then when it actually comes to the comparison with theory, we compare to 3 theories that are all really not applicable, because none of the theories have this finite domain effect that we have in terms of the lab experiments. We can only hope that they work in sort of a large rotation limit where maybe the flow locally doesn't feel the boundaries. And we have these 3 results. One is what we call an unforced steady model. So this is a theoretical expression for the Lagrangian mean velocity averaged over inertial circulations, so steady in other words, and averaged over waves, so double over bar, as a function of the Stokes drift at z is 0. And there's a solution for that. You can entirely parameterize it in terms of the Ekman number if you set z is 0, and you normalize by the Stokes drift. Then everything is a function of the Ekman number. This is a different Ekman number from what you're used to. It's a wave Ekman number. The wave Ekman number is helpfully defined as an inverse Ekman number. Intuition is wrong sometimes, then that would be why people call this the wave Ekman number. It's basically the rotation rate of the table divided by 4 times the viscosity. So k is the wave number. So that's the wave Ekman number, which is an inverse Ekman. There's a problem with this because it's singular in the 0 rotation limit to actually predict infinite drift. And there's work by Jan-Erik Weber from Norway, who a long time ago tried to correct that, I think at least in part. And without going into the detail of this, it's to do with the fact that the original derivation, which goes back to Longet-Higgins, doesn't really take into account the fact that the waves dissipate in the presence of viscosity. So Weber corrected that, put in some forcing that exactly compensated for that, and derived a different result. So those are the 2 ones, we call them unforced and forced. And then there is Chris's Higgins, also unsteady result, which is the counterpart to the unforced, but with time variation, but no spatial. That's the one that gives us the inertial loops. And so we put all the stuff on a graph. So what I'm showing you here is this, on the x-axis, this inverse wave Ekman number. And so 0 rotation is here. So this is the world where the lab doesn't rotate. And what I'm showing on this axis is the inertially averaged Lagrangian velocity. So the wave average and inertially circle averaged, normalized by the Stokes drift that we theoretically predict based on the amplitudes we measure. And what we show here is all the experimental results. It's quite a bit of scatter, but we generally see this really good trend is that as we basically rotate faster, we choke the flow and there's no transport and we get Stokes drift. We get anti-Stokes flow, we get no transport of the Lagrangian. So this is really quite clear evidence of that's happening. We see that for the smaller inverse wave Ekman numbers, there is a more discrepancy between the steady theories and the experiments, and some of that is to do with the unsteady effects. So that's the fact that we're always measuring half an inertial circle or a half completed inertial circle, and if you try to average that, it makes no sense. So we see better agreement if we compensate. We try to also estimate what are typical ranges that we might expect to see in the ocean. And there's a bit of discussion how to actually do that, because what's the value of viscosity? But I think if we use the value of viscosity that's representative of the ocean, typically we expect to be in this range. And you might see, well, it's actually close to 1. But if you go down here, then actually some of the theories would predict quite a bit of choking of the flow, so almost no transport left. And it's exactly in the range of ocean conditions that we don't get perfect agreement. And we can either get perfect Stokes drift, which is 1, or 40% of it. Yeah. So it seems to matter.
Ocean condition would be then turbulent viscosity.
That's what we put in this little, when we put this little bar here, we put in a turbulent sort of a 10 to the -2 or to the -3, like an eddy viscosity that's quite huge. In the analysis of the lab experiments, we use the actual water viscosity, 10 to the -6. On the left is the same graph I showed you before, and on the right is a corrected version of the graph. And the reason we correct is that I showed you in the beginning when I started my talk. go back. Is that if I do experiments in a closed flume or with wave groups, that I also get this negative Eulerian-mean flow, sometimes return flow. So I never expect to see the Stokes drift in a lab experiment. Our theory doesn't account for that, so we kind of correct after the fact, just to see what effect it could have. We do this in an ad hoc way, I'll admit. We simply shift things such that the initial experiment with no rotation has 1 on this axis. The equation is above, but it's basically, we move this so it's 1 here. So with 0 rotation, we see that Lagrange velocity equals Stokes drift. That's our correction. We force this to be right. And then we see how things agree. And it appears that if you make that correction, then there is maybe a little bit better agreement between theory and experiments. So what we actually need is a theory that properly accounts, or a numerical simulation that properly accounts for the finite domain effects. But it's promising that it might help. But compared to the large trend with Ekman number, it's maybe in the noise, because the main point here is that things decay rapidly. So that was my second question done. So we can observe the anti-Stokes drift. Then I want to go to the field. I don't do field work, so what I'm mostly going to do is predictive field work. This was actually some work that Chris and I supervised as master's students, and this is a bit of a review, which I'll move to second. So this is, many people interested in these questions are people who are interested in modeling plastic. What people typically do when modeling plastic is they do some Lagrangian simulation. So there's a huge community led by Eric van Sabia, with whom we collaborate a lot, and says that, okay, we want to now do these global maps of where plastic goes in the ocean. This could matter, right? And so what they typically do is they take some velocity field and they integrate with time using a framework that they have. And what we did is we did 3 simulations, 3 global, I'll show you some global pictures, and we sum what we think are non-wave driven currents, the Ekman and geostrophic currents. We then add to it the Stokes drift, the way you shouldn't, but many people do. And then we have a third simulation where we add these wave-driven Eulerian currents, which are these Ekman-Stokes flows, these things that make things go at an angle. That's the anti-Stokes flow. That's the stuff I spent the first half of my class. We added back in just to see what effect it has at a sort of global scale. This is the source of the data. We take geostrophic currents, Ekman currents from all sorts of databases, which is typically what happens. We also take wave field parameters from wave-watch simulations, and we do this at spatial resolutions of about 1/2 or 1/4 degree globally. We resolve in time, 24 or 3-hour time steps, and these are all the sources. We do these try and make these global maps. The big thing is then what value of viscosity to put in. We never really thought when we did the derivation, we kind of said, okay, well, it's just a constant nu, what do you actually put in? So we took 2 approaches. One is we put in quite a large value, 10⁻², representative maybe ocean, so it's a sort of simplest possible turbulent parameterization. We have a bit of a problem that leads to a lot of excessive transport, which I think is boundary layer streaming or something of that nature near the equator. We hack that, we fix it, we kind of get rid of it. And the second approach is a so-called Miller-Yamada model, which we also apply, which gives us this viscosity field which we implement. So we try to not do anything too controversial there, just to see what happens. So these are some pictures of what happens. This is a 10-year simulation, and this is the average velocity that you might get over that period of time. They call these, I think you probably have seen many more pictures in your lives than I have, climatologies, sometimes what people used to refer to these global maps over long term. First is of the Stokes drift. So that's the forcing to the system, if you like. So you see the familiar patterns of winds basically and waves in that direction. So you see that's kind of what the Stokes drift looks like on average on the Earth. And then we have here, so this is the US. Here we have the UE, Eulerian contributions, but only those arising from the waves. Only those computed with Chris Higgins's kernel, assuming a constant viscosity everywhere, 10⁻², or this Miller-Yamada model. And And basically what you see, it's not so straightforward to compare these, but what you see is a lot of opposing. So you see here arrows up to the right, arrows up to the left. So we see anti-Stokes flow. We see also deflection. Also the sum of this, so this the sum of basically this and this becomes that, this and this becomes that. So it's kind of two different viscosity parameterizations. So the final Lagrangian transport is the one you should really look at, and typically it has the same direction predominantly as well. It's at least positive in the same so say here it's positive, still positive, but it's reduced in magnitude. But there are also places where the deflection angle is substantial and visible. Typically the transport towards the poles is eliminated. And then this picture, which is a nice way to sort of sum it up. So we kind of wrote a response, if you like, to a paper by Oenig et al., who simply added the Stokes drift to the global simulation and said, okay, that's what it does. So they started with this simulation without any wave effects. And this picture here is a color map of the final plastic accumulation that arises after 10 years of transport when you start with a uniform initial distribution. So it leads to these garbage patches that people talked about maybe 5 to 10 years ago a lot. And then they said if you add the Stokes drift, you remove some of the garbage patches. You kind of disperse them, which was their result. And you also, you add the Stokes drift, you get lots more transport towards the Arctic. You see Antarctic and Arctic, you see. But if you add either, these are the constant eddy viscosity, that's that Miller-Yamada model. If you, bit of difference, basically you return much more to the original picture. So you kind of qualify the Stokes drift contribution because you create these Stokes-Ekman spirals. And so there's more eddies, there's more sort of accumulation patterns here than there is there. So basically our advice was never to look at this, which might have been obvious to some people already, but wasn't to some of the classic modelers. Now, that's prediction. Has anyone ever observed the anti-Stokes flow in the ocean? In the deep ocean? Probably not. I've not really seen it, it's too hard. But in the coastal zone, there is actually clear evidence. So I'll try and review that evidence a little bit. So this is a picture by Lenz from Woods Hole. They did a series of papers around the 2008s, and this is a theoretical picture. I should explain this picture from the paper. They have confusingly, this is the offshore direction. So the waves travel from right to left. I always had them the other way around. So now the Stokes drift would be to the left. And the picture they show is of the Eulerian-mean flow that arises in the coastal zone that they would expect typically. And typically, I said in my lab experiments, this would have been a depth uniform, because in lab experiments there isn't much mixing. Typically in a coastal environment, they observe this parabolic profile, which people have come up with different eddy parameterizations to predict that. But then they took some field measurements and said there were certain circumstances where they didn't see that parabolic profile. That this left picture is just explained by the presence of turbulence, but no rotation of the Earth. But then if they looked at a picture on the right, this is the anti-Stokes picture. Because Stokes drift is now positive, has this exponential shape in the opposite direction with the sign change. And then when they actually, so this is their little picture, when they actually looked at some measurements, so they actually measured the Eulerian-mean velocity as a function of depth here on this axis, and they did it for a couple of different wave conditions. They compared it to a model that includes the Stokes-Coriolis force. So this is the Eulerian-mean velocity. Remember, waves are in the negative x direction, so this would have been negative in most of my talk, but it's actually positive here. And they say that during weak winds, wave-driven cross-shelf velocity profiles, so if in the direction of the waves, in the opposite direction, over the inner shelf have maximum values of 1 to 6 centimeters a second, and vertical shear near the surface, and weak flow in the lower half of the water column. The observed offshore flow profiles do not resemble the parabolic profiles with maximum flow in mid-depth observed within the surf zone. Instead, the vertical stricture is similar to the Stokes drift velocity profile, but with the opposite direction. So that's the anti-Stokes flow that I think there is evidence for in this near shore environment. Around the same time, there's also a series of papers by Fabrice Ardouin which take into account the Stokes Coriolis, but the analysis is a little bit less obvious in terms of whether it matters or not. Right. So we thought, okay, we must go to finite depth with this because that's where it might matter. We follow what matters in life, sometimes accidentally, sometimes deliberately. So try to develop finite depth versions of the theoretical results I showed. And I'll show you a bit of a preview as to where we got to. And then finally, I'll show you some preview of lab experiments. So if we take the original equation set that I began, the one that Chris solved all those years ago, we have this Eulerian-mean, this momentum equation that we saw. We had the wave stress equation at the surface. But now if you do this thing at finite depth, not only does the Stokes drift change because it's finite depth, but also you get a bottom boundary condition that you have to take into account. This is known as bottom boundary layer streaming. This effect causes all the sand on the bottom of the ocean to move mostly. It's very important to people who are interested in sand and morphology. It's the wave-driven boundary layer at the bottom that's forced by the Stokes drift. And that is a boundary condition to this problem, so we needed to include it. Mind you, these boundary conditions are always really applied just outside of the boundary layer. So just outside of the surface boundary layer, just underneath and just above the bottom boundary layer. So if we do the same exercise, we solve the kernel. We can solve the kernel, won't look at the equations, look at the picture. So here we see a picture. I see the legend is here. So this is that kernel, the oscillating sort of inward curve. This was the deep one, the one I showed you before. And now we have a finite water depth as well. So the main conclusion is that it's not quite shallow, but it's a finite water depth. It's not so different initially, but after some time, the blue line actually converges more quickly. So there's more dissipation in finite water depth, effectively, of the flow. And so the inertial circles are more rapidly damped, which is a combined effect of the actual shallower water depth. Basically, you have a compressed boundary layer, but also the bottom boundary layer streaming has a large role in damping the flow field. So this is a slightly overwhelming picture. Series of pictures of what the mean solution looks like, the steady solution in finite depth. There's an original paper on that. To start you off, look at the picture on the left, on the bottom. So this is deep water. Only look at the left-hand side. Left-hand side is the x direction, which is the direction of the waves, and the right-hand side is the y, but only look at that. Here you see this anti-Stokes kind of solution, and you see it for different Ekman numbers. You see the Lagrangian velocity here. You see if you go to finite depth, this is KH is 1, you also see, basically in the middle of the flow, there isn't much transport. You see that the surface is still dominated by forward transport, and also the bottom is dominated by forward transport. So this is kind of the work of the boundary layers. I think that's as much as I'll say about that, because I think it's nice to also look at this picture. So if we look at a suddenly imposed forcing, we have a Stokes drift that is 0 initially, and then constant Stokes drift. So suddenly imposed constant. Typically, the response of the Eulerian is this oscillation. So you have the Eulerian is this oscillation, and here we show it for a couple of different Ekman numbers, a couple of different KHs. But the main conclusion is that the lifetime of these inertial oscillations varies very, very strongly with KH for low KH. So basically, there's a really rapid decay of inertial oscillations in the coastal zone, but in deeper water it's less. So if you ever expect to see inertial oscillations, it's in deeper water, probably not in the coastal zone. Wave-driven inertial oscillation. There's also a dependence on Ekman number where we think 100 is probably the largest it can take. So these are half-lives, I think normalized by F, but One more thing about unsteadiness. What's important is the unsteadiness of the forcing, and here we do again a Gaussian storm. So we make a Gaussian Stokes drift. So you start on the bottom left, we have 24-hour storm, 36-hour storm, 48 and 96. So 4 storms that have different durations. And then here are the Ekman-Stokes responses. And it matters a lot in terms of getting inertial oscillations, how long the storm is. If we take a really long storm, 96 hours, then basically the system can respond. It doesn't really have to shed all these waves. So you see that the UE has almost no wave signature, very small. Whereas if you have shorter storms, you get a lot of inertial response. So the length of the forcing variation is important because ultimately it's sort of a spring mass damper system. And you're trying to, if you're trying to hit something, you're trying to get it to resonate or not, and it's kind of overdamped or underdamped. That sort of analysis you can apply. I'll take maybe a couple of more minutes. So that's the effect of unsteadiness and finite depth. So now we return to our facility and I'll show you some really preliminary experimental results just to see what flow we might get. And this is Ethan kindly paid for my dinner last night, and but he now has to do some more work for my present, so he has to help. And you have to help me analyze this result, because not all of it makes sense to me, so I need some help. So this is what an experiment typically looks like. I showed you some exciting videos earlier where this thing spins really rapidly, but the idea is that it spins so slowly that the waves, which have periods of about a second, are not really meaningfully affected, but the mean flow is. And got black curtain over it because we're taking PIV measurements here. We're trying to actually resolve the whole water column. So we have this setup that we have with 4 cameras. Use fluorescent particles in the flow. We put lighting at the bottom so that we can actually, here you can see clearly the sort of where the light comes from. So we can resolve the flow field in terms of following particles in 3 dimensions. A normal PIV setup wouldn't work here because that typically is a light sheet, and we expect motions that are moving because of the waves in the XZ plane, but also because of the Coriolis effect. It also moves in the Y plane. So to track a particle, you really need to work in 3 dimensions here. So that's what a typical experiment might look like. You see the free surface clearly here. I think if that plays. Those are some raw images. So the software can track these particles. I think this is one without rotation, I think.
What's the color?
The color is actually, in this case, it's the velocity. I think it's the velocity in the horizontal direction, although don't believe it. It's a velocity, let's say, because the software has different coordinate systems from the ones we usually. So that's typically what we get out. In this domain, we get the trajectories, meaning we know the velocities, we know the spatial locations of the particles, and this is one without Coriolis. You see that the motions are pretty much in the vertical plane. Then we do a lot of processing, and maybe what I'll show you is the late time results. I'll skip the early time results. So these are the late time results. So we let this table rotate. We then turn on the waves and we wait for a long period of time. So what I'm going to show you is a deep water wave to begin with. And I'm going to show you results that are not rotating on the left and rotating on the right. So not rotating, rotating. And what I'm going to show you, what's on the x-axis, z-axis is depth, helpfully 0 here is the base. This is the undisturbed free surface at 175. It's the Lagrangian velocity that we show here. And first of all, if it's not rotating, we have all of the results, which are the experimental results, which kind of lie on this line, which is formed by the Stokes drift plus this depth uniform return flow. So it works, in deep water works quite well. Surface is a little bit difficult, but I think there's no time for that. And then, so that's without rotation, right? So up to maybe 20, 25 millimeters per second. We turn on rotation, we do the same experiment, and we see that the shaded zone is now the inertial oscillation, because you can no longer have really one particle velocity because it oscillates. If you average over the inertial oscillation, you get the brightly colored lines here. So you see pretty much the main result is that things are 0, very close to 0, and we haven't really yet looked at comparison with experiments. So this is one set of results. Now we have a similar set of results for finite water depth. Finite water depth on the left without rotation, on the right with rotation. And you see that on the left, this is at different times that we're measuring. So 15 seconds, so there's after about an hour of experiments, we see even without rotation, this is not steady. So we see that the Lagrangian velocity, although the Stokes drift is completely steady, the waves don't change, that the Eulerian-mean flow changes over time. So there's a lot of basically complex, you might call it boundary layer formation, complex behavior going on. And the theoretical result that exists for this setup is the Longwood-Higgins 1953 result, which is the purple line, which maybe has this sort of shape with the irrotational solution in red. So there's excessive transport near the surface, but there's a lot of complex physics going on if you do such an experiment. And the only sort of saving grace is that if we turn on rotation, things become a whole lot simpler. So if we turn on rotation, admittedly we rotate quickly. So this thing is that most of this flow, if you look at the magnitudes here going from between -5 and 20, the wave field is the same. So a lot of the flow velocities become very, very, very small. So there's a lot of anti-Stokes. Anti-Stokes would be 0. There is a small negative flow. There's still some positive transport near the surface and here in the bottom boundary layer that can't be killed by the rotation. But this is what's happening. There's a big open question in terms of we measure with PIV the Lagrangian velocity, but we also put these trace particles in. With PIV, we can't get that close to the surface. The trace particles are about 3 millimeters, and we find it difficult to basically square them up. So the diamond shapes are the surface measurements, and then the continuous lines end somewhere where we get our last particle. So it's really difficult still, we're beginning to analyze this, to line those up, meaning there's probably a lot of physics that happens in that top 3-4 millimeters where the wave stress is, where there might actually be a lot of local shear that you probably do need to think about. And that's exactly, I think, a layer that we've ignored in our calculation. It was this thin viscous layer in the initial sketches, but that's where a lot of submerged particles and a lot of drift happen. So I think it's important, but really hard experimentally to measure. With that, I think I should conclude. These are some of the conclusions I'd like to draw. First of all, surface waves drive Ekman-like flows, and their unsteadiness matters. We have wave-driven inertial oscillations. It matters for drift. Don't look at Stokes drift alone. Unsteadiness is less important in finite water depth. In terms of field evidence, there's no blue water evidence, so no deep water evidence of the anti-Stokes flow, but in the nearshore there is under certain circumstances. It's very sensitive to the value of eddy viscosity and the way turbulence is modeled, which in our theoretical models is clearly not the best way of doing it. Because of scale and viscosity, if you do lab experiments, might not be insightful for the real ocean because your viscosities are just so different, turbulent versus laminar. And be very careful with the wave stress, be very careful with the thin viscous boundary layer, because typically the solutions are not even valid in them, or there are solutions valid inside the boundary layer, but no one actually plots them. But that's where the drifting material typically set is placed. And I think the answer to this would come from trying to really think carefully about where the momentum goes in a proper ocean atmosphere coupled system, which is something that's also of interest to you. These are some of the papers. I think I should thank you for your attention and open the floor to questions.